kids. Today we're going to talk about the periodic table and the families associated with the periodic table. Much of this material is probably something that you've seen before in previous classes because the periodic table is stuff that's covered earlier in your academic career. However, there will be plenty of new stuff buried or scattered throughout the PowerPoint, so we will have an opportunity to learn some new stuff. Anyways, our current periodic table, or a much more detailed one, happens to lie right here. We are missing the elements that happen to be down here at 117 and 118, but I wouldn't worry about those because we're not going to deal with anything that happens to be larger than element 92, and we'll get to that guy. Starting off, and that's just a cool little display, we'll talk about that later, but the periodic table is basically broken down into three main categories: your metals, your nonmetals, and your metalloids. We're going to go through and talk about each of those a little more in depth, but the location of where to find each of those is kind of important. Your metals are all located on the left-hand side. Okay, so everything on the left is a metal except for hydrogen. Okay, hydrogen is not a metal. All of your nonmetals, okay, so the metals, this guy, all of your nonmetals are located to the far right side of the periodic table, including the hydrogen that happens to be at the top left, and we'll very, very soon discuss why hydrogen happens to be located over there. The metalloids, on the other hand, kind of share properties of both the metals and nonmetals, and they form this staircase between the elements of boron and tellurium. So this little staircase kind of working its way down represents the metalloids. Anyways, kind of when we look at metal a little more in depth, we know they're found on the left side of the periodic table, and again, except for hydrogen, because it's not. Okay, so hydrogen is not. Oh, that looks like a terrible H. And metals themselves are great conductors of heat electricity, and you should know that because all the wiring in your house happens to be made of metals, generally copper or aluminum. And all your pots and pans, the things that are going to really conduct heat in the kitchen, happen to be made of metals. Metals tend to be shiny, and they tend to be ductile, which means they stretch into very thin wires, which becomes very useful again when we talk electricity. And they happen to be malleable, which means they can be pounded into very thin sheets. And a can of something is a great example of being malleable. And basically, a chemical property of metals is that it happens to have a reaction with water that can result in rust or corrosion. So most metals can go through and rust or corrode or change color, and I'm sure you've seen that within steel or tin or iron or copper that we happen to use in class when we did the separation of mixtures lab. Working our way over to the nonmetals, which Bieber is most certainly nonmetal. These guys are found on the right side of the periodic table, but we need to remember to include hydrogen. Okay, hydrogen is included. All right, and nonmetals themselves are basically have the opposite properties of metals. They're very poor conductors of heat and electricity. Okay, they are not ductile and malleable, which means it's very hard to shape them. If they happen to be solid, they are very, very brittle and break easily, kind of like I don't know, a chocolate bar would snap. Okay, or a graham cracker, better example. But mostly, they don't happen to be solid. Most of your nonmetals happen to be gases. If you go through and look back to the periodic table, that top right-hand portion is all gases. I mean, your nitrogen, your oxygen, your fluorine, your chlorine, all of the noble gases. So out of all the nonmetals, 3/4 of them happen to be nonmetals. Or sorry, 3/4 of the nonmetals happen to be gases. So that's why they don't conduct electricity or heat very well, and it's kind of hard to shape them. Metalloids, on the other hand, happen to fall between metals and nonmetals. Okay, they are located on that little staircase, working their way down from here to here. Okay, and they happen to have properties that are both like metals and nonmetals. They can be shiny or they can be dull. They are ductile and malleable, but not nearly as well as metals. And they conduct heat and electricity very well, but not as well as other metals. Many of your metalloids, like silicon for instance, are very, very good for use in electronics because of their ability to go through and conduct electricity and charges. Okay. So what we're going to do is we're going to kind of look at how the periodic table is organized, if that ever pops up. There we go. So basically we go through and we categorize it in a couple ways. If we look side to side, we're categorizing them, the elements, into periods, which is basically what we call a horizontal row. And each period does not have similar properties. So just because they're to the left or right of a different element doesn't mean that they share any properties with those elements. Up and down, on the other hand, is what we call a family. Okay, and being above or below a given element means that you are going to have very similar properties of that element. So everything that happens to be in this green column right now has a very similar property. Everything that happens to be in this green column happens to have a very similar property. And we're going to get into how to name those individual families. Family names are going to be very key to what we do today. We don't go through and name the periods. Okay. Anyways, we talked about the idea that a period is basically just a row, okay, going side to side, and they are not alike in properties. Now, they do have a couple similarities. First off, they have the exact same energy level, and that basically just means there's the same amount of shells around the electron. So for instance, if we start off at our lithium here, we know lithium is going to have the 2 valence electrons on the inner shell, and you're going to have 1 on the outer shell. Where if I change this up and said, alright, I didn't want to do lithium, I want to do beryllium. Beryllium is going to just have 1 more electron on that outer shell. So they have the same number of energy levels. And if we changed up, instead of beryllium, we wanted to go to aluminum. If I went through and turned this into aluminum, we add a 3rd one. Okay, so it's the same number of energy levels. We also know that when we talk about different periods, the first element to the left, so these guys, always happen to be a very extremely active solid that are not found by themselves in nature often, if not at all. Okay. The last column over here, and we'll talk about the names, happen to be very inactive gases called the noble gases. And as you travel from that left column all the way to the right column, we're going to increase the protons by 1. So we increase the protons every single time. So the number of protons in the nucleus by 1. So the only real characteristics of periods is that they have the same energy levels, and as we move right, we increase the number of protons by 1. Families, on the other hand, happen to have very, very, very similar properties. Okay, and we're going to go through and we'll talk through some of the names and characteristics of each one. But when we get to a family, every single one in that family is going to have the same number of valence electrons. If I go through and I talk about your alkali metals, okay, I can start off with, we're not going to start with hydrogen, lithium and sodium and potassium and rubidium. Each one of these have 1 valence electron. And if you go through and think about our Lewis dot diagrams, they all are the exact same shaping on the Lewis dot diagrams, the outer shell. Okay, so they have the exact same number of valence electrons. That's key. The second important thing is that as you move down, because there's an increased energy level, technically the elements or the atoms have more and more energy in them. So this has 1 shell, well this has 2 shells, and this has 3 shells, and 4 shells, and 5, and 6, and 7. And as you work your way down, the more and more and more shells you have, the more energy levels we have, the more energy, because as you remember, the further away from the nucleus you are, the more energy you're going to have. Okay, so let's jump in and actually look at some of these families. Okay, and before we even do that, let's talk about hydrogen, because it's a little bit of a wild card. Hydrogen sits at the top of family 1. If we look back to this guy, hydrogen is, come on, hydrogen is here. Okay, why is it necessarily grouped with them? Because it happens to have 1 electron in its outer energy level, and because it has 1 electron in its valence shell, it happens to fit in with the rest of the alkali metals. Okay, so hydrogen does not actually become involved with the alkali metals, but it's grouped with them because it reacts similarly because of its 1 valence electron. So the 1 valence electron is very key. Valence electron. Okay, and hydrogen is kind of cool because it only needs 2 electrons to fill up its valence shell. So all hydrogen really wants to do is gain 1 electron. Okay, and it'll generally do that through bonding in covalent bonds, which we'll talk about later. Anyways, looking on the families, I would take a second, I would pause, and I would make sure your periodic table reflects the same naming on this. So go ahead, bust out your colored periodic table, your green sheet, your blue sheet, your pink sheet, your yellow sheet, whatever it is this year. Go through and actually grab that thing out so that you can label the periodic families. So give it a pause. So let's actually look through some of these families. And we're going to start off with, apparently it's not clicking through, the valence electrons of each family. One of the major points that's going to continue hitting us is that as you continue to work your way through, each family has its own set number of valence electrons. Okay, so all of our alkali metals are always going to have one valence electron. So everything in that family has one valence electron. Everything in the alkali earth metals has two valence electrons. Everything in the what do we got? Boron family has three three valence electrons. Everything in the carbon family has four, etc., etc., etc. The only real weird one about it is your transition metals, and these guys have a variable number of valence electrons, basically anywhere from 1 to 8. Okay, so we're going to kind of ignore the transition metals for the most part in terms of valence electrons. We'll use them a little bit when we get to bonding, but you do need to know and have memorized the valence electrons for each family. So we'll kick through this. Basically, group 1, your alkali members, and remember that hydrogen is not a member. It happens to be non-metal. These guys have one electron in the outer shell, which means one valence electron. Okay, and they happen to often react with the halogen family because it has 7 valence electrons, and that's because 1 plus 7 equals 8, which is a very magical number of electrons that we're going to look at later. Your alkali metals happen to be very, very reactive with water, to the point that they must be stored in oil, and they are almost never found in nature by themselves because they are so incredibly reactive. They actually kind of blow up when you combine them with water. Your second group, or second family, happens to be the alkaline earth metals. Okay, these guys have 2 electrons on their outer shell, which again means 2 valence electrons, and you should know that. These happen to be less reactive than the alkali metals, but they're still very reactive, and these guys will often react with the oxygen family, and that's because the oxygen family has 6 valence electrons, and when you add the 2 and the 6 together, again we get that key number of 8. Working our way to the transition metals, we're going to kind of spend less time on these because they're a little more complicated, but this is group 3 through 12, that middle block that's kind of set lower. They happen to be great conductors of heat and electricity, and they've been used historically for wiring for tools, jewelry, decorative metalwork, basically anything that you're using metal for, or a metal you recognize, it's in the transition metals. Their valence electrons and their oxidation numbers can vary. For instance, copper can have 1, 2, 3, or 4 valence electrons depending on which version we have. And we'll talk about those a little later when we get to bonding. Because they happen to be in the d-block orbital, which you've talked about a little bit, they can bond in a variety of different shapes. Okay. When we get ourselves down to, moving our way past the transition metals, we've got the boron family, and again, most of these are metals, except for boron itself, which is a metalloid. Okay, so it's the first time we see a metalloid. Group 14 and 15, it's the carbon family on the left and the nitrogen family on the right. So these 3 are the first, are really the big ones where we've got the name of the top element is the name of the family itself. And again, the carbon family and nitrogen family really don't have anything too special about them at our level, with the exception that all 3 of them happen to have a metal, a metalloid, and a non-metal involved in those families. Moving over to the oxygen family, our last self-titled family. These happen to contain metals, nonmetals, and metalloids. I think it's your last metalloid, actually. And these generally, again, react with the alkali earth metals. We talked about that because they happen to have 2 valence electrons. Okay. And then your halogen gases are very reactive with that first group, the alkali metals, because they have 7 valence electrons and want to get to that 8. And all of your halogen gases are non-metals. Okay? And then the last one is your noble gas family, and these all exist as gases, and they do not react because they all have an outer full shell, and that's including 8 valence electrons, with the exception of helium that has only 2 valence electrons, but it's only got that one shell. And our rare earth metals are the lanthanides and the actinides, and we're not going to deal with them in this class.